So I started to record, and we are working on parametrics today. So a parametric equation, or equations, right, is equations that are of another variable. So all this time, we've had y is a function of x is a function of t, but we've never had a situation where we had y is a function of t and x is a function of t at the same time. And so you were just talking about your statics class, so I know you've seen this sort of stuff before. We're talking about the relationship between positions of motion. I'm trying to find a marker here. Here we go. All right. So typically we would be talking about the connection between, say, an x and a y coordinate with respect to time, for instance. That would be the most used version of a parametric set of equations. And so this first example here just asks us to graph the parametric curves using a table of values. So we've got x equals and y equals, and they're both functions of t. So this is t cubed plus 1. This is t minus 2. So if I want a table of values, I need x, I need y, and I need t. So this time I'm plugging in values of t and I'm getting back x and y's. So let's choose -2, -1, 0, 1, and 2, right? The most common choices. So let's see, -2 cubed, 8 plus 1 is 9. -2 minus 2, well, actually, yeah, we'll go ahead and do it that, and then I'll explain that in a second. -2 minus 2, that's -4. Plug in -1, we're going to get 0 and -3. Plug in 0, we're going to get 1 and -2. Plug in 1, 2, -1, and plug in 2. We get that. Okay. So let's plot that in the xy plane. So I've got x equals anywhere from 0 to 9. Okay, and y is anywhere between -4 and 0. Alright, so x is 9, y is -4, 0, y is -3, x is 1, y is -2, when x is 2, this is -1, and when x is 9 again, we get 0. This one's wrong up here, sorry. Just wondering why that was funky. -2 cubed is -8. So that'd be what, -7? It's going to do something like this. Okay, so that's a rough graph using just a few values of t. We can do this on our calculator as well. And we can do that by, once again, going to our mode. And if you look on the fourth option down, see if I can get this on here with some light. So fourth option down, the second one there says parametric. So I'm on function right now. If I go over 1 and hit enter, I'm now in parametric mode. So when I hit y equals, you'll notice I get an x1 and a y1. I'll just enter in the equations for x and y. And then make sure my window is standard, so zoom 6. Now on this graph, it only gives me here on. Okay. The reason for that is because the calculator believes that there's no way for t to be 0 or to be less than 0. So it believes that these 2 points do not exist. The reason for that is because t, as I said, normally represents time, and there's no way for us to go back in time. So in most cases, t equals 0 is going to be where you start, and you can't go beyond that. But in other cases, right, t does not always represent time, so I'm okay if you go back beyond 0. All right. So the next part says, can we eliminate the parameter? Well, of course we can. Right, so we've got 2 equations here that are both functions of t. So for instance, I could solve this equation right here for t, plug it into that one. Okay. And the question is, well, why would we want to do that? Well, our end goal is to get a function that is an equation of both y and x, not t. Right? We're trying to eliminate that middleman, basically. So again, for instance, if we're talking about some kind of physics problem, if we're talking about some particle moving through the air, we don't necessarily want the height with respect to time, or the range with respect to time, but rather we want to know what is the height when I am 30 feet away, right? So Tom, you said where was t in that graph? That graph was not a function of t, right? That was using the x and y coordinates. So that's eliminating the parameter. And the graph that you just did on the calculator does the same thing. That is an xy graph. All right, so let's see if we can't figure out how to do these next couple. It says, write each parametric equation as a Cartesian equation, then graph each curve and indicate the direction. So time can be represented by the direction on the xy curve. So I'm given x equal t, y equal t squared minus 1, and interval from 0 to 8. So eliminate the parameter. This one's super easy. X is equivalent to t, therefore I can just substitute x in here. And immediately I get an equation, y is a function of x. That is a parabola facing upward that's been shifted down 1 unit. If we're starting at 0, this portion is no longer there. And t goes just like x. Right, so as t increases, if t is 1, x is 1, t is 2, x is 2. Therefore, the direction is that. So we put arrows to represent the direction. Tom, you said, is this a branch of differential equations? There is a section in differential equations where you'll learn how to solve parametric differential equations, or a system of parametric equations. But this is not necessarily a derivative from. Looks awfully fuzzy. There we go. A little better. So let's look at B. B is x equal e to the t, y equals e to the minus t. And t greater than or equal to 0. Okay. So again, you have to try to think to yourself, okay, how can I get this into a y equals a function of x? Well, the first thing I thought to do was to rewrite y as 1 over e to the t. And therefore, if x is equal to e to the t, then y equals 1 over x. And that's one of those parent functions, so you should know exactly what that looks like. Should look something like this. And I need to get my arrow off of here because my direction is that way. All right, it doesn't continue on forever that way either. All right, so these were very simple. This was a direct substitution. This one almost direct substitution. Another way I've seen people do that one, they've multiplied these two, and you get e to the 0, which is 1. Solve for y, you still get 1 over x. All right. What's the difference between this and a simple systems of equations? So the system of equations, we're trying to solve for x and y. Here we're just trying to get a function of y with respect to x so that we can plot the two. right? These still both have dependency on time, but we can, so they call it eliminating the parameter, so that we can say, okay, I don't necessarily need to know, what is my y position at time t equals 5, but I do want to know what the x position is when y is 7, that sort of thing. So there are two equations that are related by a third variable, and we're getting rid of the third variable. All right, what else do we got here? All right, this next one is 3 sine squared t y is equal to 3 cosine squared. And again, this one is over 0 to 2 pi. So, anybody have a suggestion on how to put these two equations together to get just x and y? So yeah, that's the Pythagorean identity. Right, if I add the two together, right, x plus y is equal to 3 sine squared plus 3 cosine squared. That's 3 times the quantity sine squared plus cosine squared. And sine squared plus cosine squared, we should all know, is 1. So we get x plus y equal 3, and if you want a y equals equation, 3 minus x. So it's not always, let's just take x equation, solve it for t, and plug into the other one. That's not always the best route. This would have gotten quite ugly, and instead we've turned it into something quite nice. So just as a heads up, the main reason that we're doing parametrics is because next we're going to be doing polar. And there are certain things that are easier to graph in polar than they are in Cartesian. And those things are typically circles. So I've got the equation y equal 3 minus x. If I were to graph that, it would look something like this. Right, it has to intersect at 3, and it's got a negative slope of 1. Now the reason I stopped at the axes is because when x is 0, right, what happens? What is my coordinate? Or sorry, when t is 0. When t is 0, we get x is 0, y is 3. So we start there. When t is, let's say, pi over 2, well, then we get 3, and we get 0. So then we're down here. And those are really our extremes, right? Because if I pick some number in between here, these aren't going to get any bigger. Right, sine squared and cosine squared are still maxed out by 1. And so if I plug in 0 for the first one, then I get a 1 for this part. If I plug in pi over 2, I get a 1 for that part. So those are my endpoints. But just from 0 to pi over 2, I went all the way down there. But then, if I let, say, t equal pi, well, sine of pi, 0. Cosine pi is -1, squared is +1. So we're back up here. So it looks like I went down, and then I'm heading back up. So this is a weird one because it's got both directions. So what just happened? Well, we converted a x and y equation that were dependent on t, that were oscillatory functions, right, sine and cosine, that bounce back and forth between, in this case, because they're squared, between 0 and 1, and we turned it into a line, which means if we have a direction, well, it's going to do that oscillatory motion, right? It's going to bounce back and forth. So yes, you are correct. All right, let's try the next one. So again, I have sine and cosine. Again, I have to try and get rid of the t somehow. It's not going to really help me to solve this for t and plug it in there, because then I'm going to have the cosine of the inverse sine. And none of us know what that looks like, right? So another tactic, notice that we had a Pythagorean identity here. Well, what if I just squared both of them and then added them together? So x squared is going to be sine squared. Y squared is going to be cosine squared. Is there a glare there? Okay, we're still all right. And then again, sine squared plus cosine squared is 1. What is this the equation of? So we could solve it that way. But I'm thinking it looks more relatable to you in that form. So yeah, that's an equation of a circle, right? X squared plus y squared equals r squared. So this is the unit circle. The only thing we need to do is indicate direction. So where do we start? Well, if we set t equals 0, we get 0 and 1 as our starting point. So up here. We let t equal pi over 2. Sine is 1. Cosine is 0. If I go to pi, then I get 0, -1. So it appears I'm going around this way. So one thing to note, and I hope I don't confuse you here, t equals 0, which looks like it's an angle, right, because we're plugging it into sines and cosines, did not correspond to that point. This was t equals 0, it's t equal pi over 2, it's t equal pi. That would be 3 pi over 2. It's still blurry. All right, so we're starting to learn a couple different ways to do these. This last one's a little tricky. X equal 2 sine t. Y equals 3 cosine t. Okay? And same bound, 0 to 2 pi. Now, I say this is a little tricky because almost all students want to immediately square it and add it together, just like the previous example. But if I do that, I'm going to get 4 and 9 as my coefficients. And I need to be able to get just sine squared and cosine squared with no coefficient at all. So that doesn't help me. So what I should do first is divide both sides by that constant. Then square both sides. And add them together. Okay, so x over 2 squared is equal to sine squared. Y over 3 squared is equal to cosine squared. Add them together. Sine squared plus cosine squared is 1. This is x over, well, let's just leave it that way. Does anybody recognize that equation? Not quite. So if you look at it, it looks quite a bit like the one we had last time, right? That was a circle. But there's something different here. So yeah, an ellipse. And this one has a radius of 3 in this direction, and a radius of 2 in the other. And again, we just need to show the direction. So the exact same setup, it's sine and cosines, so it would run the same direction. So any questions about how to eliminate the parameter, how we figure out the direction, any of those things? And so just as a recap, right, we had a direct substitution. We had where we could square both sides and add them together. Once in a while you can maybe divide the two equations, stuff like that. Alright, so I'm going to continue, and if you guys still have questions, feel free to ask them. So that was a nice exercise, but we are doing calculus, so that's really what we want to do. So we're now going to do some calculus with parametric equations. And we need two major formulas for that. The first is the first derivative. Which says if I want dy dx, then I need to divide dy dt by dx dt. And it should be clear that dx dt cannot be 0 here. Otherwise we'd be dividing by 0. So that's the first derivative. And the second derivative is the derivative with respect to x, no, with respect to t, of the first derivative divided by the x dt, if I remember correctly. What does that mean, Parthy? Here we go again. You don't like derivatives of parametric equations? Or the fact that we're now actually going to do calculus? Alright. So it says, find the equation of the tangent line and find where the graph has horizontal and vertical tangents. All that being the first derivative test, or first derivative that we need. So, problem 1, x equals t squared minus 3 y is equal to t to the fourth plus t. And given point, t equal -1. So the first part asks, can we find the equation of the line tangent to the curve? So we need the slope, which is the first derivative. So I need dy dt, that would be 4t cubed plus 1 divided by dx dt, which is 2t. And we can find a number for that by plugging in t equal -1. So 4 times -1 cubed plus 1, 2 times -1. So it looks like 3/2, if I'm not losing it. That's our slope. Of course, we need our x and y values at t equal -1. So x of -1, -1 squared minus 3, that's -2. And y of -1 is -1 to the fourth plus a -1, which is 0. So if we want the tangent line, we use our point slope formula. That would be y minus 0 equals the slope, 3/2, times x minus a -2. So that looks like our equation. So that is the tangent line to the curve in the Cartesian plane created when you eliminate the parameter here or plot these as a parametric curve. So in your calculator, when you plot these, it gives you the curve in the xy plane. So that would be the tangent to that curve. Otherwise, you'd have to have two plots, right? You'd have to have x as a function of t and y as a function of t. So that's part A. Part B says find where the graph has horizontal and vertical tangents. Okay, well here's our derivative for a horizontal tangent. What are we doing? So if we want horizontal, right, that's where slope is 0. So we really only care where 4t cubed plus 1 is 0. Which would be that. Now that is a negative time, so if we were not considering time to be negative, that would be a problem, but we were given t equal -1 to begin with, so we're okay. However, as I was saying earlier, when you plot these curves in your calculator, you won't be able to see the point where this is the tangent. So you'd have to do this by hand or on another program, or just plot it as a y equals equation. So anyhow, that would be horizontal value of t. If you really wanted, you could plug it back into x. And whatever that comes out as would be your x coordinate for the horizontal tangents. And if you wanted the vertical tangents, or sorry, vertical tangents, then we would say when is the denominator 0, and that occurs at t equals 0. And for x, that is -3. So that's one thing we could ask. We could say we've got parametric equations, find the tangent line at a point, tell me where it's got horizontal and vertical tangents. And that all requires just the first derivative. Okay. So I think I'm going to save B for you guys. I may put that on that assignment. I'm going to go ahead and do the next problem, which says determine the intervals for which the parametric functions are increasing and decreasing and are concave up and concave down. Okay. So x is equal to square root of t. I'm just going to go ahead and write that as t to the 1/2. And y is equal to 1/4 t squared minus 4. Okay. So part A is increasing and decreasing. We should know that that's the first derivative test. So I need dy dx. And I get that by taking the derivative of t to the 1/2. And I'm going to put that on the bottom. So that's 1/2 t to the minus 1/2. And on top, I need dy dt. I'd bring the 2 down in front. So that's 1/4 times 2t. Simplifying, 1/4 divided by 1/2 is going to be let's see, we're going to flip and multiply. So 1/2, or I guess we could just do this. 1/2 for 1/2 is 1. T over t to the minus 1/2. That is t times t to the 1/2, or t to the 3/2. So it looked really ugly, or it looked like it could be ugly, and turns out not so bad. That's my first derivative. So to find the increasing and decreasing portions, I need to set this to 0 and solve for t. Well, that only gives me t equals 0. And let's say for this problem, t has to be greater than or equal to 0. So we'd only have to test positive t's. Right, if this is t equals 0, we can't have anything over here. We would pick a test point on this side. So I let 1 equal my test point. 1 to the 3/2 power is positive. So this thing is increasing for 0 to infinity. And that is both on t and x, depending on what you want. Right, t and x are only, or they're related by the square root. So all these are positive, which means the same thing would occur for x. But this, when I write these currently, I'm doing them in terms of t. So this is increasing from 0 to infinity for t, decreasing never. Okay. We want to know concave up and concave down. So I need the second derivative. That's here. That's going to be the derivative with respect to t of the first derivative, which is t to the 3/2, divided by dx dt, which was 1/2 t to the minus 1/2. Derivative of this guy is 3/2 t to the 1/2 over 1/2 t to the minus 1/2. This division here, you would multiply by 2, and you would get 3. And t to the 1/2 times t to the minus 1/2, or divide by t to the minus 1/2 is t. Remember, you subtract exponents, so it'd be 1/2 minus a negative 1/2. You'd add those together and get 1. Okay. So my second derivative is 3t. So then I want to say, okay, when is it concave up and concave down? Again, set it to 0, and I get t is 0. Test points. I really only need 1 on that side again, because I've restricted my values of t here. If I plug t equal 1 in, I get a positive number out of that, so it looks like it's concave up from 0 to infinity. Again, that is good for both t and x. The only way that they wouldn't be the same is if they had some strange relationship, like, I mean, even just x equal 1 over t, right? t being 0 is a problem. So it's increasing and concave up both from 0 to infinity. Any questions about that problem? Realistically, the only thing we have to do here is just follow the equations that were given. Everything else is all stuff we've learned already. Okay, so I'm going to go ahead and continue. We have one more topic, and then we can call it an early day. This topic is looking at the arc length of a parametric curve. So the arc length equation is given as integral square root, just like before, but instead of 1 plus, we've now got dx dt squared plus dy dt squared. And now here we have dt from some a to b. So in the screen or off the screen? All right, so you can't see the b, but that's not a big deal. So again, we have the equation. We're given the problem. Find the arc length of x equal 3 plus 3t, y equals, so this is 3t squared, y equals 4 plus, is that 3t? No, 2t cubed. Okay, so I need dx dt, and I need dy dt. So dx dt is the derivative of this function, which looks like 6t. dy dt looks like 6t squared. So now I need to plug both of these into the formula. And our bounds here were zero to 1. So I need square root. This is 6t quantity squared plus 6t squared quantity squared dt. So I don't know how you would go about doing this. I guess I'll just write it all out. It's 36t squared plus 36t to the fourth Notice they both have a 36t squared in common. Pull that out. Left behind I have a 1 and a t squared. 36t squared is the same thing as the quantity 6t squared. So these two things can come out of the radical as a 6t, but they still must stay within the integral. At least the t does. Okay. And then this is a basic u substitution. If I let u equal 1 plus t squared, du is 2t dt. Well, I can break 6 into 2 times 3. And so this is 3 integral of u, or u to the 1/2 du. Because u is everything under the radicals, so you get square root of u, and then 2t dt is your du. So I just left the bounds off for a second because we have to change them. So t is 0, u is equal to 1, and when t is 1, u is equal to 2. Okay, write that as u to the 1/2. Integrate that, you get that. All right, you add 1 to the power, so 1/2 plus 1, that's 3/2. And then divide by 3/2, same thing as multiplying by 2/3. So get rid of these 3's. 2 times, plug in 2 to the 3/2 minus 1 to the 3/2. There's not a whole lot you can do there, unless you wanted to get a decimal answer. So again, as soon as I took these derivatives and plugged them in, this was all review. Any questions about that guy? All right, so I'm not seeing any questions. So I'm going to assume you guys are good. Go on to the last problem. Right. So these are our two functions. It tells us to go from 0 to 3. I need to find dx dt, dy dt, and I need to plug them in and square them. Dx dt is going to be e to the t minus e to the t, or e to the minus t. And dy dt is going to be minus 2. So I have square root e to the t minus e to the minus t squared plus a negative 2 squared. Thinking we're going to have to go ahead and FOIL that guy out there. So e to the 2t minus 2 times this times this. So if I multiply these, I would add the exponents, and they would add to 0. So e to the 0 is 1. And then this guy squared would be plus, and then that up there would be minus 2t. And then over here, I'm going to have plus 2 dt. Actually, plus 4. Silly me. So, this is 0 to 3, square root, e to the 2t, negative 2 plus 4 is plus 2. And I wrote it that way because my hope was that you see that it's the exact same thing, just with a different sign. Which means it factors the same, but with a plus sign. So then we have a quantity squared, square rooted. So now we've really got just that. And the integral for that guy is e to the t minus e to the minus t from 0 to 3. So again, not a nice, neat, cute answer at the end, but one nonetheless. So, questions? Did I go too quick? Do you understand what's going on? Anything? All right, great, guys. So I'm going to go ahead and stop the recording.